we are going to learn about the marginal probability distributions. And rather than assuming a discrete joint probability mass function, we integrate a continuous joint probability density function. Why? Because this is the continuous random variable case, okay? And if the joint probability density function of continuous random variables x and y is given by the following equation, fxy, x comma y, the marginal probability density functions of x and y can be expressed by the following equation, okay? In the previous discrete random variable case, the marginal distribution of x was the summation of the joint probability mass function, right? But in this case, we are going to discuss about the continuous random variable case. So the summation should be transferred to the integration, okay? But in here, in the case of the marginal probability density function of x, should be integrate of the joint probability density function by y, okay? Also, the marginal probability density function of y should be equal to the integration of the joint probability density function over x, okay? So this is the relationship of the marginal probability density function with the joint probability density function. And this is the example of the marginal probability density function. For the random variables that denote times, in the previous example 5-12, what is the probability that y exceeds 2000? This is the case of the marginal probability density function, right? We are going to discuss about only y, okay? So, for this example, we need to calculate the probability of y when y is larger than 2000, okay? But to solve this, in the previous class, we drew this diagram. That is, this is the random variable x, and this is the random variable y. And we can say this is the relationship y is equal to x, okay? And in the previous example 5-12, y should be larger than x, okay? That is the requirement. So that means only this shaded area can be considered, right? Because y is always larger than x, okay? And in the case, the question was y should be larger than 2000. And we can say this is the 2000. And then we need to calculate this shaded area, right? For this question, okay? And in here, we are going to divide this part into two parts. And we can say this is the part A and this is part B, okay? And the reason why we have to divide this zone will be explained, will be understood in the later explanation. And first we are going to calculate the part A, okay? And for the case of the part A, we need to provide the double integration, right? And the joint probability density function was 6 by 10 to minus 6 by exponential minus 0.001x minus 0.002y and dy and dx, right? Okay? In this case, in the case of the part A, the y should be larger than 2000, right? So the range should be between 2000 and infinite, right? In the case of the y. And what about the x? Since this is the y is equal to x, right? This point should be also 2000, right? So the x should be smaller than 2000, right? Because A is this shaded area. Okay? So for the x, that should be between 0 to 2000. Okay? Since the random variables x and y denote the time, there will be no minus time, which means that the x should be larger than 0. Okay? So if we say that this is small a, okay, and a is equal to 6 by 10 to minus 6 power by exponential minus 0.001x by integration from 2000 to infinite exponential minus 0.002y dy. Okay? And this can be rewritten as 6 by 10 to minus 6 power by exponential minus 0.001x by minus exponential minus 0.002y over 0.002 from 2000 to infinite. Okay? And this can be changed to 0.003, right? By exponential minus 0.001x, okay? By, what is the exponential minus infinite? That is 0. And plus exponential 0.002 by 2000 is equal to minus 4. Okay? So this is equal to 0.003 by exponential minus 4 by exponential minus 0.001x. Okay? This is for the case of the small a. So the a is equal to the integration from 0 to 2000 and 0.003 by exponential minus 4 by exponential minus 0.001x dx, right? And this is equal to 0.003 by exponential minus 4 by minus exponential minus 0.001x over 0.001 from 0 to 2. And this can be changed to 3, okay, by exponential minus 4 by minus exponential 2, okay, right? And plus, what is exponential 0? That is equal to 1, okay? So if you solve this equation based on the scientific calculator, you guys gonna be obtain .0475. Okay? 0.0475. So the A is equal to 0.0475. Okay? And then we are going to calculate the zone B. This should be also double integration, right? And we are going to apply the identical joint probability density function, that is 6 by 10 to minus 6 power by exponential minus 0.001x minus 0.002y dy and dx. But in this case, the zone B here, the y always should be larger than x, right? Okay? So, the zone, this integration should be from x to infinite, right? Because this zone, the y should be always larger than x, right? So, the starting point of this integration should be from x to infinite. But in this case, the x always should be larger than 2000, right? Because the zone is from 2000 to infinite. Okay? So, what about the x? That should be from 2000 to infinite. Okay? So, we need to calculate this equation. In here, we are going to calculate this part first. We can say this is the small b, and small b is equal to 6 by 10 to minus 6 power by exponential minus 0.001x by minus exponential minus 0.002y over 0.002 from x to infinite. Okay? And this is equal to 0.003 by exponential minus 0.001x by minus 0 plus exponential minus 0.002x. Okay? Okay? So, this is 0.003 by exponential minus 0.003x. So, this will be the integration from 2000 to infinite 0.003 by exponential minus 0.00 dx. Okay? That is equal to 0.003 minus exponential minus 0.003 x over 0.003 from 2000 to infinite. Okay? And this can be eliminated. So the answer is minus 0 plus exponential minus 6. Right? So this is equal to exponential minus 6. And the exponential minus 6 will be 0.0025. So this is equal to 0.0025. So finally, the probability of y when y is larger than 2000 will be the summation of 0.0475 plus 0.0025, okay? That is equal to 0.05. Okay? So that is the answer for this question. And now, I'm going to explain about the conditional probability distributions for a case of two continuous random variables. And similar to the previous discrete random variables, we can define the conditional probability distribution of y given x when x is equal to small x. And given the continuous random variables x and y with joint probability density functions fxy, x comma y, the conditional probability density function of y given x is expressed by this equation. And we have already learned about this. This is the conditional probability of y given x, right? And this should be equal to, this is the joint probability density function, right? And over, this is the marginal probability density function of x, okay? So this is exactly identical equation with the previous discrete random variable case. Do you remember that? But we only use the integration instead of the summation. But the concept is identical. And in here, the marginal probability density function of x should be larger than 0. Why? Because this is used for the denominator for this equation, okay? So this is exactly identical with the discrete case. And the conditional probability density function fy given x satisfies the following properties. The first one is that this conditional probability density function should be larger than or equal to 0, right? And secondly, if you integrate this conditional probability density function, this should be equal to 1 for all y in the region Rx, including all x, okay? Which means that we are considering all x and all y, okay? Thirdly, the conditional probability of y, when y is included in a set B, given x, should be equal to the integration of the conditional probability of y, okay, over the region B. Okay? And this can be understood from the following example. Okay? So this should be satisfied for any set B in the range of y. Okay? So this is the example 5-13. And for the random variables that denote times in the previous example 5-12, determine the conditional probability density function for y given x when x is equal to small x. That is the example. That is the question. The marginal probability, the conditional probability density function of y given x, y is equal to the joint probability density function of xy over the marginal probability density function of x, right? We all know about this equation. Right? So, to calculate the conditional probability density function, we first calculate the marginal probability density function of x, right? Because in the previous example 5-12, the joint probability density function was given. So, we have to calculate the marginal probability density function of x to calculate the conditional probability density function, okay? So, we have to calculate the marginal probability density function of x. And what is this? That is the integration of the joint probability density function over what? the previous slide, we have already learned about this, right? At the beginning of this class. So, this can be written as in the previous example 5-12, the x should be larger than, y should be larger than x, right? Which means that this should be the integration from x to infinite, right? And 6 by 10 to minus 6 power by exponential minus 0.001x minus 0.002y by, right? Okay? And this can be rewritten as, this part can be extracted, right, from the integration. So 6 by 10 to minus 6 power by exponential minus 0.001x by integration from x to infinite exponential minus 0.002y by. Okay? That is equal to 6 by 10 to minus 6 power by exponential minus 0.001x by minus exponential minus 0.002y over 0.002 from x to infinite. And this can be rewritten as 0.003 by exponential minus 0.003x, right? So, this is the marginal probability density function of x, okay? Then, now we can calculate the conditional probability density function of y given x. That is equal to 6 by 10 to minus 6 power by exponential minus 0.001x minus 0.002y, okay? This is the joint probability density function. And also, this is the marginal probability density function, 0.003 by exponential minus 0.003x. Okay? And what is this? That is 0.002. Okay? By exponential. What about this? That is exponential 0.002x. And minus 0.002y. So, this is the conditional probability density function of y given x. Okay? And in this case, x always should be 0 and y always should be larger than x. That is the requirement. And in this case, what is the probability that x exceeds 2000 given that y exceeds 2000 given that x is equal to 1500. For this question was the probability of y, right? Y should be larger than 2000, right? Given x is equal to 1500. Okay? And what is this? this is this relationship, right? The y is included a set b, which is the larger than 2000, okay? Given x, when x is equal to 1500. So we can use this equation in here. So there should be integration over set b, right? That is from 2000 to infinity. Okay? And also, this part should be the conditional probability of y given x, y, dy. Right? And what is this? We already calculated here. Okay? This is the conditional probability density function. So, this can be rewritten as 0.002 by exponential 0.002 x minus 0.002 y dy. Okay? But from the question, x is equal to 1500, which means that this can be written as 0.002 by 1500. Okay? What is that? That is equal to 3. Okay? So this can be written as 3 by exponential minus 0.002 y. Okay? So this will be 0.002 by exponential to third power by minus exponential minus 0.002 y over 0.002 from 2000 to infinite. Okay? And this can be eliminated. And what is the exponential minus infinite? That's 0. So exponential 3 by minus 0 plus exponential minus 4. Okay? So the final answer is equal to exponential minus 1. That is 0.368. Okay? So this is the answer for the question. So to calculate the joint probability density function of y when y is included a set, we first calculate the conditional probability density functions. Okay? Because we have to use this relationship. And now, I'm going to explain about the conditional mean and variance. Conditional mean of y given x when x is equal to small x denoted as large E, large y given x or mu y given x. Okay? And this can be expressed by the following equation, that is the integration of y multiplied by the conditional probability density function of y given x. Okay? And this is exactly identical formulation with the previous this case, but the summation is just changed to the integration. And the conditional variance of y given x denoted as large V, large y given x or sigma square y given x can be expressed by this equation. Okay? The integration of y minus, this is the conditional mean, square by the conditional probability density function. And this is also the identical formulation with the previous discrete case, but the summation is just changed to the integration because this is the continuous random variable case. So we can use both equations to solve the conditional mean and the conditional variance for the case of the continuous random variable. And this is the example. For the random variables that denote times in the previous example 5-12, determine for y given that x is equal to 1500. That is the question. And for this question, we need to calculate the large E, large Y, given 1500, right? And this should be equal to the integration y multiplied by the conditional probability density function of y given x dy. Okay? And what about this? What is this? That is equal to the integration from where? X, right? Because in the previous example 5-12, y is larger than x. So in this case, the starting point is from x, okay? To infinite y by 6. What is the conditional probability density function of y given x? That is equal to this equation, right? So that is 0.002 by exponential 0.002 x minus 0.002 y ui. Okay? So we need to calculate, but here the x is equal to 1500, which means that this can be written as 3 by exponential minus 0.002y, okay? And this can be written as 0.002 by exponential 3, okay? Exponential to third power by integration from x to infinite y by exponential minus 0.002y dy. Okay? So in here we need to calculate this integration. We can say this is a. And here, to calculate this equation, we need to use the very famous relationship. That is, the integration u by dv over dx is equal to u multiplied by v minus integration v by du over dx. Okay? We need to use this relationship. And for this relationship, we can say u is equal to y. Okay? But here, we use the y instead of x, which means that we can change these two y, okay? So, what about du over dy? That is equal to 1, okay? And in here, dv over dy is equal to exponential minus 0.002y. So, v is equal to minus exponential minus 0.002y over 0.002. Okay? So, based on this relationship, we can be written as a is equal to y multiplied by 3 is equal to minus exponential minus 0.002 y over 0.002 from x to infinite, okay, minus integration from x to infinite v is equal to minus exponential minus 0.002 over 0.002 by dv over dy is equal to 1, okay? So, dy, okay? And in here, this is equal to infinite, okay, by exponential minus infinite or 0.002, okay, minus x minus exponential minus 0.002 x over 0.002. Right? Okay? But here, we need to use the L'Hopital's rule. That is, the limit when x goes to infinite, x by exponential minus x. Okay? This is equal to the limit when x goes to infinite, x over exponential minus x, and based on the L'Hopital's rule, this is equal to the limit when x goes to infinite 1 over exponential minus x. Okay? Okay? That is the L'Hopital's law. Changing the limit when x goes to infinite, x over minus x, to the limit x goes to infinite 1 over exponential minus x. That is the L'Hopital's rule, okay? Oh, sorry, this is x, okay? And what about this? That is equal to 1 over infinite. That is equal to 0, okay? So, based on this L'Hopital's rule, what is this? That is equal to 0, okay? Okay? So, finally, this part is equal to x by exponential minus 0.002 x over 0.002. Okay? So, we can simply express this equation to this. And also, what about this? This can be plus, right? So, this is equal to plus minus exponential minus 0.002 y over 0.002 from x to infinite. And what is this? 0 minus 0 plus exponential minus 0.002x over 0.002, right? Okay? So, this is equal to the exponential minus 0.002 over 0.002 squared. Okay? So this is the small a. Okay? Okay? 이거 적분해 보면 되죠. 그죠? 근데 익스펜셜 마이너스 인피니트 0이니까. 그죠? 요것만 남습니다. So now we calculate sorry, this should be 1500, right? Right? Because this question, x is equal to 1500. Okay? So the x should be changed to 1500. Sorry. Okay? And this can be 1500 and this is equal to 1500. Okay? So this part I'm going to calculate again. The first part goes to 0, right? Based on the L'Hopital's law. So the second part will be 1500 by, so that is equal to 0 minus 1500 by minus exponential 3, okay, over 0.002, right? Okay? Oh, sorry. Okay? This, right? And plus, this is minus exponential minus 0.002 y over 0.002 square, right? From 1500 to infinite, okay? So this is equal to 1500 by exponential minus 3 over 0.002 plus minus 0 plus exponential minus 3 over 0.002 square. And this is equal to 1500 by 2 by exponential minus 3 plus exponential minus 3, right? Okay? And that is equal to 3. So the answer is 4 by exponential minus 3 over 0.002 square. Okay? Okay? So here we calculate the small a. Okay? So the answer should be 0.002 by exponential 3 by 4 by exponential minus 3 over 0.002 square. and exponential can be eliminated. Okay? And this can be eliminated. So 4 or 0.02. Okay? So the final answer is 2000 millisecond. Okay? So this is quite complicated, but based on this concept, we can solve the problem. 아시겠죠? So this is about the examples of the conditional mean. And now I'm going to explain about the independence. Okay? The properties of the independence. For the random variables x and y, if any one of the following properties is true, the others are also true, then x and y are independent. The first one is that the joint probability density function of xy should be equal to the multiplication of each marginal probability density function. Okay? That is the first case. And secondly, the conditional probability density function of y given x should be equal to the marginal probability density function of y for all x and y. But in this case, this equation is equal to the joint probability density function over the marginal probability density function of x, right? So that's why the marginal probability density function of x should be larger than 0, okay? And thirdly, the conditional probability density function of x given y is equal to also the marginal probability density function of x for all x and y, but marginal probability function of y should be larger than 0. And this is the last relationship, that is the probability of x when x is included a set A and y is included a set B should be equal to the multiplication of each probability, okay, for any set A and B in the range of x and y respectively. And also the identical with the previous discrete case, okay? And this is the example 5-17 about the independent random variables. And the previous example 5-12 is now modified. Just x and y is larger than 0, okay? And this relationship is not satisfied anymore, okay? For this question. And so the joint probability density function of x and y is given the following equation. The joint probability density function is now modified to 2 by 10 to minus 6 power by exponential minus 0.001x minus 0.002y, okay? And in this question, show that x and y are independent. That is the first question. And then determine the probability of x when x is larger than 1000 and y is smaller than 1000. Okay? These are two examples. So first we are going to verify that the random variables x and y are independent. So for this, we have to make sure that this is equal to the multiplication of each marginal probability density function, right? So they should be equal to the marginal probability density function of x by the marginal probability density function of y. Okay? So what about the marginal probability density function of x? They should be equal to the integration from 0 to infinite, and 2 by 10 to minus 6 power by exponential minus 0.001x minus 0.002y dy. Okay? Right? And this can be written as 2 by 10 to minus 6 power by exponential minus 0.001x by minus exponential minus 0.002y over 0.002 from 0 to infinite. Okay? And this can be eliminated, and 0.001 is left by, and this is gonna be 1, right? So that is 0.001 by exponential minus 0.001x. Okay? And the marginal probability density function of y is equal to the integration from x to infinite, right? Why? Because the example is now modified, which means that x comma y is larger than 0, and this relationship is eliminated. Okay? So this is from 0 to infinite, and 2 by 10 to minus 6 power by exponential minus 0.001x minus 0.002y dx, right? And this is equal to 2 by 10 to minus 6 power by exponential minus 0.002y by minus exponential minus 0.001x over 0.001 from 0 to infinite. What is this? 1, right? So this is equal to, this should be first eliminated. So 0.002 by exponential minus 0.002y. Okay? So if we multiply these two equations, that is equal to 0.001 by exponential minus 0.001x by 0.002 by exponential minus 0.002y. That is equal to 2 by 10 to minus 6 power by exponential minus 0.001x minus 0.002y. So we verify that this equation is independent. Okay? The random variables x and y are independent. Okay? Because the joint probability density function is equal to the multiplication of each marginal probability density functions. And we need to determine the probability of x when x is larger than 1000 and y is smaller than 1000. So this is the case of the independence, which means that the probability of x when x is larger than 1000, y is smaller than 1000, is equal to the multiplication of each probability. Right? Because this is the independence. Okay? And so, the probability of x when x is larger than 1000 is equal to the integration from 1000 to infinite and the marginal probability density function of x. Right? Right? So, that is equal to the integration from 1000 to infinite. This is the marginal probability density function of x. Okay? So, 0.001 by exponential minus 0.001x dx. Okay? Okay? So, that is equal to 0.001 by minus exponential minus 0.001x over 0.001 from 1000 to infinite. Okay? This can be eliminated. And what is this? That is exponential minus 1. Okay? So, it is equal to, this is just exponential minus 1. Okay? Because we need to calculate this one as well. And what about the probability of y when y is smaller than 1000? That is equal to the integration from 0 to 1000, right? And the marginal probability density function of y is equal to this equation, right? So, that is equal to 0.002 by exponential minus 0.002y dy. Okay? And this is equal to 0.002 by minus exponential minus 0.002 y over 2 from 0 to 1000. This can be eliminated first. And this is equal to minus exponential minus 2 plus 1. Okay? Okay? So, the final answer is exponential minus 1 by 1 minus exponential minus 2. And if we use the scientific calculator, that is equal to 0.318. Okay? Okay? And so, if the two random variables are independent, this relationship, this problem can be simply calculated based on this equation. And this is another example. Example 5-18 about the machine dimensions. Where the random variables x and y denote the length of two dimensions of the machined part. And assume that x and y are independent and follow normal distribution, okay? And the means and variances of the random variables are given as the following table, Okay? Random variables x and y follows the normal distribution. And also, the mean is equal to 10.5 for the case of the x and 3.2 for the case of y. And the variance is 0.0025 for the case of x and 0.0036 for the case of y. And in this case, what is the probability that x is between 10.4 and 10.6 and y is between 3.15 and 3.25? That is the question. Okay? So we need to calculate this relationship, this equation. X is between 10.4 and 10.6, comma, y is between 3.15, 3.25. Okay? But the question was that we can assume that the x and y are independent, which means that this is equal to the multiplication of each probability. Okay? And the question said that the random variables x and y follow the normal distribution, which means that we can use the standard normal random variables to use the appendix table. Okay? And also, the example gave the mean and variance. So, we can use the standard normal random variable z, the probability z between 10.4 minus, what is the mean? Mean is 10.5, right? Over this should be the standard deviation. So, this is the variance. What is the standard deviation? That is the root variance. So, that is equal to 0.05, right? And this is also between 10.6 minus 10.5 over 0.05 by the probability of z when z is between 3.15 minus, what is the mean? That is 3.2 here, okay? 3.2 over, what is the root 0.0036? That is 0.06, right? And also, this will be 3.25 minus 3.2 over 0.06. Okay? And this is about the standard normal random variable. Okay? Because the random variables are following the normal distribution. So this is equal to the probability of minus 2 and plus 2, right? By the probability of minus 0.8 between 0.833. Okay? And this can be written as the probability of z when z is smaller than 2 minus the probability of z when z is smaller than minus 2. Okay, do you remember that? By the probability of z when z is smaller than 0.833, okay, minus the probability of z when z is smaller than minus 0. Okay. So this is equal to, if we use the appendix table, and that is equal to 0.9772250 minus 0.0183095 0.79 6731 minus 0.20329. Okay? And if you calculate this, the answer is equal to 0.568. Okay? So, in the case that if the random variables following the normal distribution and also they are independent, we can use the standard normal random variable, and also we can simply calculate this kind of problem. Okay? And we have learned about two continuous random variables up to this slide, but we are going to learn about the multiple continuous random variable cases. Okay? So this is the joint probability density function for the case of the multiple random variables. The joint probability density function for the continuous random variables x1, x2, x3, blah 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 xp, denoted by the following equation: f x1, x2, xp, and x1 comma x2 comma blah 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 xp. And this joint probability density function satisfies the following properties. The first one is that the joint probability density function should be larger than or equal to 0. Okay? For all variables, this is wrong. Okay? From x1 to xp. Okay? And this be for all okay. This should be changed to this. Okay. And secondly, the integration from minus infinite to infinite of the joint probability density function should be equal to 1, right? For all random variables. And thirdly, for any reason B of p-dimensional space, if the probability that the x1, x2, xp are included in a zone B, reason B, should be equal to integration of B. Okay? Do you remember the previous case that for the case of two continuous random variables, we have already learned about this concept, right? But in this case, the number of random variables is increased from 2 to infinite, okay? 2 to multiple cases. So we can use the same concept, okay, with the previous case. And this is the example 5-20. This is time is over, so this is end of today's class. So we are going to learn about this example from the next class, okay, next Wednesday.